Howdy! This is your friendly neighborhood physics teacher here, and this week we're going to talk about waves. So there are different types of waves, but we're just going to focus on just waves overall. We'll get in more specific with sound and light weeks to come. So waves. What is a wave? A wave is a disturbance that transfers energy. So it carries energy from one place to another. Now, a lot of people think like a wave, if you think about like a water, like waves crashing on the beach, they think that the particles themselves, like the water particles, actually move. And they don't. And hopefully we'll be able to see that as the notes, as we go through the notes. But so they carry energy from one place to another. They carry energy, not material. So the key thing here is they carry energy. Oh, not what I wanted to do. I wanted to be able to rate. So they carry energy. That is the big thing that they do. They carry energy. So classified by what they move through. So there's two big things, different types of waves. So think about, you have waves, and then you can break it down into two other categories. So you have mechanical waves, which energy is transferred by vibrations of medium. So medium is matter, so like water, solids, liquids, gas, so you have to have some type of medium. So you have to have a solid, a liquid, or a gas to for the wave to be able to move. Then you have your electromagnetic waves, which energy can move through anything. And they actually move through the electromagnetic field. It makes its own field. So that's why these can move through space, and actually solids, liquids, and gas get in their way. It slows them down. So your mechanical waves need material. Your electromagnetics do not like material because it blocks it. An example of your mechanical waves would be sound. That's why you don't hear sound in space, because there's no material in space. And your electromagnetic waves would be an example of light. That's why, you see, it's a really pretty sunny day outside, but you don't know that until you open up a window, because your walls block the sunlight. So let's focus on mechanical waves real quick. So these require a medium. Now remember, medium is just a material. So going back to medium, it's a solid, liquid, or gas. So those are your mediums. And it's to transfer the energy. So they travel through, it travels through. And in a perfect world, there would be no loss of energy. Energy would be conserved. It would stay in the string. It would stay in the spring. It would stay in the water, and you would not lose any of that energy. But, real world comes into play and actually loses energy over time. Again, you have some examples of water, sound, rope, spring waves, anything like that. So we have a string here, and you sit there and you pulse a spring, and so it's just making one little tiny pulse, and it's moving. Now, what I want you to pay attention to is the string itself. So the string itself is attached. If I can make it attached. Yeah, the string itself is attached. So the string is not moving except from going up and then eventually back down when the pulse goes by. So the string is only moving up and down. It is not moving side to side. So the string itself is not moving side to side. It's only moving up and down. So that's a big thing with mechanical energies. It's not actually moving the particles. Every time you go knock on the door, it's not like the particle of the door that's on the front gets pushed to the center or anything. It just doesn't work that way. It's only the vibrations of the little materials transfer that energy. So you have so we're looking at mechanical energy. You can break it down even more. So we have the pulse, which you saw with the string. So it directs energy. Vibrations, which that'd be like you knocking on something and you're sitting there and the particles I hit start to vibrate, and then they continue to vibrate, and so on and so forth. And you have three different types. You have longitudinal, which you can't really see, but you kind of see in this little area right here where the particles kind of scrunch up. And then you have the transverse, which the whole entire object starts to do a up and down motion. That's the, if I tell you to like draw a wave, that's what most people tend to draw as a transverse wave. And then the surface wave is just a transverse wave that only happens on the top. So this would be more like your ocean waves or surface waves. And so those are your three different types of your mechanical waves. Transfer waves, if you sit there and you take the string and actually move it back and forth, back and forth, back and forth. And then you have longitudinal, which these are more like sound waves. They kind of do a slinky aspect, or almost like an accordion as it scooches in and scooches out, scooches in, scooches out. So that would be your longitudinal. All these waves are also known as periodic waves, and it's just saying that it repeats. It has a pattern. So it goes up and then it goes down, and then it goes up and it goes down. It just has that continuous pattern. And that continuous pattern makes your wavelength, makes your frequency, and makes your period and certain thing like that, which we'll get into more detail in just a minute. But this repeating pattern is called a periodic wave, and all these are considered periodic waves. So the other side, so that's where all mechanical waves. So transverse waves is a vibration in the perpendicular to the direction of the motion of the wave. So remember, perpendicular means you have a 90-degree angle. And so if you are moving that way, your wave is doing that. Or, and so on and so forth. So it sideways or up and down, so it can move either way. And some examples of that are considered S-wave earthquakes. Your P waves are your longitudinal, they compress and stretch out, but your S waves, that's why it's called S, it makes an S pattern. And your electromagnetic or light waves are also transverse. And again, you have this up and down motion. Now, one thing to also remember, you still only have particles still only go up and the particles still only go down. They do not travel down the string itself. They do not do that. So they only go up and down. So the different types, big types that we're going to talk about is your electromagnetic, and we'll get into these. This is your light waves. And you'll see that reason it's called electromagnetic is because it's actually two fields that are interacting with each other. You have your magnetic field and you have your electrical field, and that's what makes light. But we'll get in that in probably about 2 or 3 weeks. Your transverse wave. Now, your electromagnetic wave is a version of a transverse wave, but this is over just transverse waves in general. And this is like where we start sitting there explaining what each part is of a wave. So we have a couple of things labeled here. Let's see if I can change my color so I kind of stand out a little bit. There we go. So your wavelength is basically exactly how it sounds. So wavelength. Feel all right. I don't know why my pen's being funky. Okay. So your wavelength is your length of the wave, basically. It's from your starting point to your end point. I said it's like a periodic wave as a repeating pattern. So basically your wavelength, if you draw a line here, if you start here and you would stop there. So it's basically your wavelength is the length of a full pattern. It's the full pattern. And you can have different versions. So you can start there. Here goes from here all the way to here. And it doesn't matter where you start or stop as long as you do one complete pattern. So your wavelength is one complete pattern. Now your wavelength, if you see it, does have a variable. So your wavelength is what you considered called a Greek letter lambda, and it's measured in meters because it is have length. So your wavelength is measured with a lambda, and it's your length, and so it's meters. Next thing is your amplitude. Your amplitude is how high your crest or how low your trough goes. So these little peaks, and yeah, I know I don't like the fact they called it peaks. So the top parts are called crest. Think about you're going over a mountain, so you're about to it's a crest. And then your trough, think about like what your animals, at least my animals, drink out of. Trough are your lower parts. And so basically it's measuring your amplitude. Your amplitude is the distance between your equilibrium. And your equilibrium is just your line right there. So that's what your equilibrium is. So the distance between your equilibrium and your crest or your trough. That is represented with a capital A, and it's also measured in meters. And we don't really get into what your amplitude is, pretty much how energetic your object is. So your amplitude tells you how energetic something is. And then, so yeah. So there we go. Got some things going on there. And then your longitudinal. So your longitudinal, as you can see, you have some areas that are very scrunched together, and you have some areas that are very spread apart. Your spread apart are called rarefactions. So rarefactions, and that would be like equivalent to your trough, and where it's all scrunched, it's called compressions. It's called compression. So spread out is refractions, where it's all scrunched together is called compressions. And this again is mostly for sound, and it's just the amount of energy it's like your particles are getting really scrunched together. They're vibrate, and then they kind of spread out, and then they scrunch. They kind of, again, they do like the accordion, way of moving. So there is one equation that goes along with at least just waves in general. So the rate at which the energy travels, so you have to have speed and direction, and it depends on the medium. So mechanical waves travel faster through denser mediums. So you did hear that right. So your mechanical waves, they kind of go, right over here. So it moves fastest through solid, then it'll go liquid, and then it'll go gas, and it doesn't move at all through your vacuum of space. So it goes in that fashion. Your electromagnetic waves, so that goes to that one. So your electromagnetic waves actually go vacuum. That means like the vacuum of space, then gas, then liquid, and then solid. So your electromagnetic waves don't want mediums. They actually slow down as the medium gets thicker, unlike your mechanical waves that that slows down as your particles get farther and farther apart. The big reason is because your mechanical waves need that material. So if your materials aren't right up against each other, it takes a minute from particle to particle to particle to actually transfer. Like your electromagnetic waves that wants to go through literally goes through your mediums. So if it's a thick medium, it can't go through it. So again, you see here you have your wavelength. Remember, your wavelength is measured by meters. You have your amplitude that does your power or energy of the wave. And then going from here to here again, so one wavelength, so that's one oscillation, is frequency is number of oscillations per. So basically, how many of these wavelengths you can get in 1 second is frequency. And frequency is represented by, so let's write this down. So frequency is, your variable for that is a really fancy looking F, and your units is hertz for frequency. Your units is hertz. And your frequency does have another equation that you can use to solve for it. So your frequency equals 1 over your period. And basically what your period is how, so this is like frequency is the number of oscillations in 1 second. Your period is how long it takes to do one oscillation. So that's why it's kind of opposite. So your T is period. And again, so frequency is that. Your period is how time for one oscillation. That's your time for one oscillation. You can actually turn this into a triangle. So you have your V, and you have wavelength, and you have frequency. And then, so there you go. So if you're covering up your velocity, you get wavelength times frequency. Cover up your wavelength, you get velocity divided by frequency. Wavelength equals velocity divided by frequency. And if you're looking for frequency, you're just going to get velocity divided by wavelength. So there you go. Kind of breaking down the equation there. So you do have, we've been talking about light and sound. We'll get into that. Sound will be next week. Light will probably be the week after that. And so just a couple of things to know, that your speed of sound in air, and I specifically said air because it's different, but that's what we listen to is in air, is about 330 meters per second. The reason I said it's about is because if it gets hotter or colder, it does affect it. So we'll go into that with sound later. And then your speed of light in a vacuum, again, if it's in air or in liquid, that's going to slow it down. But speed of light in a vacuum is 3 times 10 to the 8th meters per second squared. And so everyone's like, when you hear people talking about the speed of light or anything like that, it is talking about your 3.0 times 10 to the 8th. So hopefully that helps, gets you a little bit understanding about waves. And if you have any questions, please don't hesitate to ask Miss Heath or Miss Verona. Have a wonderful day. Bye.